Mathematics presents itself as a sprawling expanse of autonomous domains. A single line of inquiry bursts into specialized fields: number theory, differential manifolds, and algebraic rings. Yet practitioners across these fields encounter a paradox. Specific structural correspondences repeatedly surface in unrelated contexts. An algebraic invariant discovered in one decade will dictate the constraints of a topological space in the next. Traditional foundations typically view these as isolated silos. In this fragmented view, a concept like closure is a local property, such as the requirement that adding two integers must result in another integer. Foundational systems like set theory or category theory focus on how one domain can be represented within another, often treating the internal diversity of mathematics as an historical accumulation. This leaves the generative source of that diversity unaddressed. Philip Lillian proposes a foundational inversion. Closure is the primitive, generative engine of mathematics. This diagram outlines the generative ontology. At the top, closure is the condition of determinacy, how a regime preserves itself. Without this, systems cannot distinguish lawful continuation from departure. Number, algebra, topology, geometry, and analysis form an ordered architecture of distinct closure regimes. Closure grounds the intelligibility and existence of these mathematical domains. We begin the structural derivation at the base of the architecture. This is where closure operates at its most resolved scale. Here we find discrete closure. Mathematical identity is preserved through exact separation. Elements remain distinct, and formation proceeds by exact, stepwise recurrence. Zero acts as the absolute baseline of admissibility, while unity functions as the first positive, stabilized discrete act. When exact distinguishability is combined with lawful succession, arithmetic form emerges. Counting is the derivative action made possible because discrete closure is already in place. Number is the first stabilized regime of closure. It provides the exact resolution required to build subsequent mathematical structures. The rigidity of discrete succession cannot account for units entering into internal combinations. To maintain coherence when elements merge, the system requires a law of composition. This forces an extension into the second tier, operational closure. At this level, admissibility is preserved under lawful transformation. Identity is maintained through invariance across operations like addition or inversion. Because the regime itself is stabilized under these operations, mathematical laws can range over formally indeterminate placeholders, giving rise to variables. Algebra is the structural form of invariant composition generated by operational closure. Operational closure governs finite combinations. But it lacks the resources to articulate infinite approach, limits, or spatial continuity. To define continuity, the organizing principle must shift from mathematical composition to mathematical adherence. This brings us to relational and limit closure. Admissibility here is determined by proximity, neighborhood, and approach. Stability at this level is achieved by including limit points, which define the interface between an interior and its boundary. Topology is the structural extension of closure required to make spatial continuity mathematically coherent. Topology maps static relations. It cannot articulate how a structure changes as it traverses across a domain. The system extends into the fourth tier, transport closure, where structures remain coherent under lawful passage. To maintain closure during movement, the regime introduces connection as the primary transport law. Any path-dependent deviation across the domain is articulated as curvature. Traditional perspectives center geometry on measurement and metrics. However, a coherent means of relating separated regions must exist before those regions can be compared. Geometry is the regime generated when closure regulates coherent movement and structured deviation. Geometry governs the transport of stabilized form. It does not regulate the internal, infinitesimal variation of the form itself. To resolve arbitrarily small variations while preserving internal coherence, closure extends to the top tier, continuous completion. Differentiation acts as the local law governing this infinitesimal variation, ensuring that local change proceeds under stable rules. Integration provides the necessary completion, accumulating those local infinitesimal changes into a global structure. Analysis represents the highest resolution regime of closure, finalizing the upward architecture. This 5-story architecture functions as a completely unified mathematical whole. This entire system relies on the principle of structural retention. Each higher regime is an ordered extension. It introduces a richer form of mediation while preserving the rules of the level below it. Continuous integration at the top is mathematically impossible without geometric transport. Geometry relies on topological boundaries. Topology relies on algebraic equations, and that dependency cascades to the discrete separation established at level 1. Mathematical diversity is a structured differentiation unified by this single architectural framework. Major breakthroughs in mathematical history can be mapped directly onto these specific closure regimes. Richard Dedekind's work on numerical completion defines the base constraints of the discrete regime. Emmy Noether formalized the mechanisms of algebraic invariance, providing the explicit structural content of operational closure. Alexander Grothendieck's reconstruction of deep geometric structure acts as a rigorous manifestation of transport closure. These historical milestones were brilliant but partial realizations of the underlying generative source. In the end, the true architectonic unity of all mathematics arises directly from the single generative engine of closure.